Okay, we've been talking chapter 13. We got into gases and we saw some relationships that are important for gases. First off, unit-wise, we have an atmosphere, which is a very common unit. That is equal to 760 millimeters of mercury, and that also equals 760 torr. As we talked about last time, pretty much those are your kind of big three units that you'll see in terms of pressure. And obviously that 760 number is an important number as that's the conversion basically between really atmospheres and millimeters of mercury are to torr. And again, a millimeter of mercury is a one-to-one relationship with a torr. So basically you just change the units on that one. So if you have atmospheres and want millimeters of mercury or torr, you're going to multiply by the 760. And if you have millimeters of mercury or torr and want atmospheres, you're going to divide by the 760. We started talking about some relationships here. We talked about Boyle's law, and that was P1 V1 equals P2 V2. Remember, this is at constant temperature. And as the pressure goes up, the volume goes down, and vice versa. Pressure down, volume up. We also saw Charles' law and Guy-Lussac's law. And that's V1 over T1 equals V2 over T2. That is at constant pressure. And as we talked about, the way it's able to really maintain constant pressure is it's the volume that adjusts. So as the temperature goes up, the volume will go up to keep the number of collisions pretty much constant. And as the temperature goes down, the volume will go down as well, also to keep the collisions constant. This gas law and pretty much all gas laws, Kelvin is the unit of temperature that you need to use. As I mentioned last time, it should be kind of like a no-brainer on that. It's probably the first thing you should do if you have a temperature value, just convert it to Kelvin because you will need it pretty much for all gas laws in Kelvin. Guy-Lussac's is P1 T1 equals P2 T2. This is at constant volume. And the relationship here is, in this case, the volume actually doesn't adjust with the temperature. So when we do see the temperature go up, we would expect the gas molecules to be flying around faster because they have more energy. And that would cause greater collisions, and we would see the pressure go up with it. And vice versa, if we lower the temperature, our gas molecules are going to fly around slower, going to result in less collisions, and we will see the pressure go down. We also had our friend Avogadro's law, which is V1N1 equals V2N2. This is at actually two situations, constant pressure and temperature. And really the relationship here is sort of as the moles go increase, so does the volume and vice versa on this one. Kind of put them all together, we get our ideal gas law, PV equals nRT. And this is the most restrictive in terms of units, and obviously Kelvin here for temperature on that guy. Pressure, when you use the ideal gas law, has to be in atmospheres, volume has to be in liters, N should be moles, and T should be our temperature in Kelvin. And that is because R is a gas constant, 0.08206, and it has units of liters, atmosphere, Kelvin, and mole. So that is why really all the other things have to be in those units so that it cancels out correctly with the gas constant. The gas constant is a value, obviously, you do need to know, and it is usually never given to you in a problem. They just, again, assume that you kind of know that you have that value available to you, and they oftentimes will not give it to you there in a problem. We also talked about STP, and remember STP is standard temperature and pressure. And it actually does stand for two values. The temperature would be 273.15 Kelvin, and the pressure is basically 1 atmosphere. So if you're given something that says at STP, those would be the values that you would use, for example, in the ideal gas law, if you needed to, or really any other gas law, like we did in that experiment the other day. There is a relationship if you're at STP, and this is, again, the only time that you can use this relationship if you have both of these conditions met. You could do 1 mole of any gas will be 22.414 liters. So what that allows you to do in some cases, especially if it's an STP condition, is you can actually use that conversion without necessarily having to use the ideal gas law. But you could actually still use the ideal gas law even if it's STP conditions. So you could always use the ideal gas law regardless of the conditions. But again, this is kind of be a shortcut in the calculation if you happen to be at STP conditions. Again, as I mentioned before, if you don't want to worry about it, you could ignore it and just always go into the ideal gas law, and you'll probably be okay. Any questions on any of that stuff there we talked about last time? All right, so I think we did one example before this, so why don't we do this one here? We got calculate the pressure in atmospheres of 32.5 grams of SF6 gas that's in a container with a volume of 252 milliliters and 45.5 degrees Celsius, sulfur 3207, and our fluorine should be about 19. All right, stick. Okay, so let's take a look. Again, as we talked about, if you kind of pull out the information, it kind of will help maybe point you in the right direction. So obviously here we're looking for a pressure. We have a mass of 32.5 grams of SF6. We do have a volume of 252 milliliters, and we do have a temperature here of 45.5 degrees Celsius. So we have a pressure, a volume, a temperature. We don't have moles, but we do have grams, which means we can get to moles. So that should really, again, point you really into the ideal gas law here, which is PV equals nRT. Again, as I mentioned before, very rarely will they ever mention the gas constant, but it is a value that you do have available to you at all times. So we do have that number available. So we do have to do a few conversions here. So first off, we do need to get our mass into moles. So we want the moles here of SF6. That will require us to go to the periodic table and calculate the molar mass of SF6. And if you do that, 1 sulfur plus 6, bless you, fluorines, looks like you get 146.1 grams per mole of SF6. That'll get you 32.5 divided by 146.1. It gets you something like 0.2225 moles of SF6. We also need to convert our volume here because it does need to be in liters when we use it in the ideal gas law. So our volume of 252 milliliters, move to decimal or divide by 1,000, your choice, gets you 0.252 liters. Lastly, like normal, our temperature here needs to be converted into Kelvin. So we're going to take our 45.5 plus a 273.15, and that's going to get us here. If I add the right number, that would get us here. I'll call it 318.7 Kelvin. Now that we got everybody in the right sort of unit, we're going to divide the volume to the other side there so we can solve for pressure. Pressure will equal nRT divided by V. Putting in our numbers, 0.225 moles. Again, our gas constant, which we always have, liters, atmosphere, Kelvin, mole. Our temperature in Kelvin, 318.7. All going to be divided by our volume, which has been converted into liters. The moles will cancel, the Kelvin will cancel, and the liters will cancel, going to leave us atmospheres as the only unit left, which is good, since we are looking for a pressure in this case. So if we multiply our moles times our R times our 318.7 divided by 252, or 0.252 would be a better way. That looks like we're going to end up with like 23.1 atmospheres in this particular case. Any questions on that one there? So again, the importance of the ideal gas law is used a lot, and really where a lot of people really do necessarily kind of screw up on it is not necessarily the rearranging, but just making sure everybody's in the right units. So that's really important when you use that formula, that everybody's put in the right units. Again, very commonly people just leave the temperature in Celsius, and sometimes we'll leave the pressures in whatever unit. So everybody needs to be kind of in those right units. Any questions on that there? All right. So the next thing we're going to talk about is what happens when we have changes in pressure, volume, and temperature. So if you actually take the ideal gas law and you basically solve it for R, which is a constant for two different conditions, that's an R and that's an R, and those are the same value, which means if those are the same value, you could actually put these two parts of the ideal gas law equal to each other, and we get this guy. In most cases, though, the moles don't change all that much. So a lot of times this will reduce down to this. And this is what is sometimes referred to as the combined gas law. And it really is from the ideal gas law, kind of just putting everybody together once you solve for R. And that is basically P1 V1 over T1 is equal to P2 V2 over T2. This is like anything else. Kelvin here, again, for our temperature. The pressure, though, in this one, it doesn't matter as long as they're the same on both sides, so everything cancels. And the same thing with the volume. As long as the volume units are the same on both sides, again, that everything will cancel out correctly. So out of all the gas laws that we learned, to be truthfully honest with you, you're going to invest your time in remembering the gas laws, which you have to anyways here. I would remember this one. And in fact, the one I would remember is the one that's really derived from the ideal gas law, which looks something like this that we saw before. P1, V1, N1, T1 is equal to P2, V2, N2, and T2. Why would I focus and remember this one? Well, frankly, from this gas law, you can pretty much get whatever gas law you need, all those other ones that we just saw. So if you come across a problem and there's no mention of moles, there's no mention of temperature, or you're told they're held constant, all you have to do is just scratch them out. And now you are staring at Boyle's law. Now, if you take this same sort of combined gas law and you come across a problem where you do not see any mention of pressure or moles, or they're held constant, all you got to do is just scratch them out. Right there's Charles' law. You take this gas law and you come across a problem where there's no mention of volume or moles, and you just scratch those guys out. Now you have Guy-Lussac's law. PV, take this gas law here and you come across a problem where there's no mention of pressure or pressure or temperature. You just scratch those guys out. And there's our friend Avogadro's law. Yeah. So really, if you just remember this equation, which is really from, again, the ideal gas law, and you basically just scratch out what's not given to you, what's held constant, you'll have pretty much all the other gas laws that we learned without having to remember each one individually. So that's a really good way to do that. And obviously, you should know how to use the ideal gas law by itself as well. So again, if you're going to invest your time, which you do need to learn all these gas laws because we're not allowed to give you any of them, I would just go with those two. And like I said, you pretty much can get all the gas laws that you would ever need. And again, basically, you're just going to scratch out anything that's not mentioned or anything that's held constant. And it should leave you really with the right gas law to use in that case. Any questions on that? Except I did write this wrong with a, that should be a T there, not a B. Any questions on that? All right. So why don't you try one here? Consider a sample of oxygen gas at 27 degrees, has a volume of 9.55 liters and a pressure of 2.97 atmospheres. The pressure is changed to 8.25 atmospheres and heated to 125 degrees Celsius. What is the new volume of the gas? So take a few moments there, see what you come up with. Okay, so again, if we pull up the information here, we have a temperature here at 27 degrees Celsius. We have a volume that is 9.55 liters, and we have a pressure that is 2.97 atmospheres. We have another pressure here that is 8.25. We also have another temperature of 125 degrees Celsius. And finally, we are looking for a volume. So again, just looking at that, that should really point you to the combined gas law, which pretty much has all those guys in it. And again, here, there's no mention of moles, so I'm not going to worry about the moles part of it. I'm just going to call the first ones the ones, the second here the twos. Like normal, we got to do our conversion here to Kelvin for our temperatures. And that means, I'll go this way, I think. We got 27 plus 273.15. Going to give us 300.15 here. And we'll do 125 plus a 273.15. We'll go a 398.15 Kelvin. Our pressure units are okay. They're both in atmosphere. So again, as long as they're in the same units, it's not an issue. In this case, we are solving for V2. Remember, as we talked about, if you move something across the equal sign here in a gas law, they end up in the opposite location, which means this guy's going to go to the top and this guy will go to the bottom when I solve for it. That will give me that V2 is equal to P1, V1, bringing the T2 to the top, divided by T1 and bringing the P2 to the bottom. Putting in our numbers, making sure we get everybody in the right spots. We got 2.97 atmospheres. We have our V1, which is 9.55 liters. And here we do have our T2, which is our 398. That's going to be divided by our T1, which is 300.15, and our P2, which is 8.25 atmospheres. Once again, the kelvins will cancel, the atmospheres will cancel. When we solve for our volume, it will be in units of liters in this case. And that's going to give us a 2.97 times 9.55 times a 398.15. 398.15, there you go. Divided by 300.15 and divided by 8.25. Going to give us a 4.56 liters in this particular case. Any questions on that one? I would say this one is the one that gives people sometimes a really hard time of rearranging and having trouble rearranging it. So just keep it simple, just opposite sides if you move it across the equal sign. Yeah. Any questions on that one there? All right, then let's talk about stoichiometry involving gases. As we touched upon last time, it's pretty much the same stuff. Again, you want your balanced equation. You want to convert to moles. You want to use the mole to mole relationship. And then you want to take those moles to some other unit. Now, it can also be a limiting reagent problem. So again, if needed, obviously you would need to do your limiting reagent calculation. The main difference here is honestly, somewhere along the way, you're going to probably use the ideal gas law in most cases. And if you use it kind of early on in the calculation, you would use it here to get moles, and you probably would be solving for PV over RT here. And also very commonly is you could use the ideal gas law here at the end once you have moles, bless you. Very commonly, if you use it at the end, most of the time I would probably say you would probably be looking for a volume and stuff like that in a lot of cases, as you would have the other sort of numbers there, pressure, temperature, and obviously the moles would come from the stoichiometry part as well. So those are two very common places where you would incorporate sort of the ideal gas on there. The rest of the sort of stoichiometry part is really the same. It's just the mole-to-mole relationship, and that's really because you have information about one thing, but you're interested in the other. So, for example, like the experiment we did last week, where you had the hydrogen gas you were interested in, um, and again, all the information you had was necessarily about the magnesium that you started with, so you had to use stoichiometry to get over there. So why don't we try one here and see what is the volume of CO2 produced at 37 degrees Celsius and 1 atmosphere when we take 5 grams of glucose are used up in this reaction. So if we were to look at this, we're looking for the volume here, basically, of this gas. What we know about it as well, since it is a gas, it does have a pressure of 1 atmosphere. It does have a temperature of 37 degrees Celsius. Remember, again, not usually given to you, but you always have R available to you. So if we think about sort of our ideal gas law, PV equals nRT, if we solve for V, which would be nRT over P, and this is for our CO2, we just kind of check off what we have up front. We have the temperature, we have the pressure, we have R. So the one kind of piece of information we're missing in this particular case to actually solve the problem is the moles of the CO2. So we have to kind of look and see what other piece of information we have. And we do have the grams of this guy. And that's really where sort of the stoichiometry is going to come into play. We're going to balance our equation, which it is balanced. We're going to take whatever we have here that we could actually get moles from and convert it into moles. So we would do that and take our 5.6 grams of C6H12O6. Once again, like we've done a number of times up to this point, we would have to go to the periodic table and get the molar mass of this guy. So that's going to be 6 times 12.01 plus 12 times 1.008 for the hydrogens, plus 6 times 16 for the oxygens. And that will give us 180.2 grams per mole of our C6H12O6. That's going to get rid of our grams and convert this into moles. And if we do that, we will end up with 0.03108 moles of C6H12O6. Now that is helpful because we do need moles for our ideal gas law, but we do need to remember we need moles of CO2. So this is where the stoichiometry part, which is our third step, comes into play. This is obviously not a limiting reagent problem at all. So we just need to do our mole-to-mole relationship. And if we look from the equation, we can see the mole-to-mole relationship between those two guys is a 1 mole of C6H12O6 gives us 6 moles of the CO2. So that's what's going to allow us to go from our reactant in this case to our product, which is what we're interested in. So that's what we would use. Again, opposites cancel, so 6 moles of CO2 up on top, the 1 mole of the C6H12O6 on the bottom. Again, that is the stoichiometry part, like we've done a number of times at this point. We're going to times that by 6, going to get us 0.1865 moles of CO2. That is the missing piece of information that we need to basically solve for the volume of CO2 that we would create. We also have to be careful, though, before we stick all those numbers into that ideal gas law, we do need to make sure everybody's in the right units. And like normal here, our temperature is not, right? Our temperature is still in Celsius. So we do need to convert our temperature into Kelvin, like pretty much normal. And if we do that there, we'll have 37 plus our 273.15, going to give us 310.15 Kelvin. Our pressure is already in atmosphere, so that is good to go. So now we could actually use that gas law. Our volume would be the moles we just solved. And again, we want to make sure we're using the moles of the CO2 here. We are going to use our R, which is a constant. We're going to use our temperature that we just converted into Kelvin, and we are going to divide all that, I'll go here to the left, by our pressure, which is 1 atmosphere. Atmospheres will cancel, Kelvin will cancel, and moles will cancel. It's going to leave us our volume in liters in this case. And if we do that, we will end up with basically 4.75 liters of CO2 in this case. Again, it really is the same sort of 4 steps that we've done in stoichiometry, balance equation, convert to moles, mole to mole relationship, and here at the end, using the ideal gas law at the very end of this calculation to basically figure out the volume. Question on those steps there. All right, I tried one. Why don't you try one maybe? All right, so what is the volume of hydrogen gas at 27 degrees Celsius and 1.25 atmospheres that's required to react with 5.65 grams of phosphorus? Phosphorus is 3097. Okay, so let's take a look. So once again here, we're looking for hydrogen gas, which obviously is a gas. So we are looking for a volume. Since that is a gas, we think gas laws. So we do have a temperature of 27 degrees. We do have a pressure of 1.25 atmospheres. And once again, we always have R that is available to us, liters, atmosphere, Kelvin, and mole. So we should really, a lot of times in a stoichiometry problem, think only really of the ideal gas law is usually most of the time, the gas law that you can probably use. Not always, but most of the time that's going to be it. So once again, if we just kind of check off, we got temperature, we got R, we got P, and we are looking for volume. That once again leaves us with needing the moles here of our hydrogen gas. We can get there by basically doing stoichiometry because we do know the amount of phosphorus we're going to put in there. So following our stoichiometry steps here, step number 1, we have an equation that's balanced. Step number 2, we do need to convert what they gave us into moles. So we're going to go periodic table there, 3097 times 4. Going to give us 123.9 grams per mole of P4. The grams will cancel, and that will get us here 0.04561 moles of P4. Remember, though, that we are looking for hydrogen gas, so that is the purpose here of the stoichiometry part of this. So that is the next thing that we need to do. If we go to the equation, we see 1 mole of our P4 gets us 6 moles of our H2. And again, that is just the coefficients. So we'll do our 1 mole of P4, giving us our 6 moles of H2. So taking our number there from above, going opposite so they cancel out correctly. P4 will go on the bottom. H2 will go up on top. So we're going to multiply by 6 here. And we multiply it by 6, 0.2737 moles of H2. That again is really the missing part that we need here to finish out the problem. Step 4, we are going to use the ideal gas law. Here we're going to solve for volume, which is very common at the end. Once again, before we go in there, we got to make sure our units are correct. So here we will add our 273.15 to convert our temperature into Kelvin like normal. And that will give us 300.15 Kelvin. Popping these numbers in will get us 0.2737 moles, or 0.08206 liters atmosphere Kelvin mole, and our 300.15 Kelvin, all divided by the pressure in this case, which is 1.25 atmospheres. Atmospheres again will cancel, moles will cancel, Kelvin will cancel. And again, here when we solve for our volume, it will be in units of liters. So if we do that math there, And we're going to get something like 5.39 liters of H2 is needed here to react with that much phosphorus. This would not be a yield as it is a reactant in this case. Yeah. Any questions on those steps? Again, same 4 steps, just incorporating really the ideal gas law in most cases.